Okay, good to see you back for lesson 33, which is the photoelectric effect. Now I thought before we'd start today's lesson, I'd just go give you a little story here first. So we'll start with the story of Sisyphus. I don't know if you know who this person is, but he was the person who was punished to have to roll a rock up a hill, and then it would fall back down. If we just kind of look at the story here, Sisyphus's task. As a punishment to the gods for his trickery, Sisyphus was made to roll a huge boulder up a steep hill. But before he could reach the top of the hill, the rock would always roll back down, forcing him to begin again. Now you can imagine this would actually suck pretty bad. For eternity, you'd have to roll a ball up or do a job, and then again, it would actually never reach the top. You'd never reach the summit. Quite frustrating, and in fact, probably enough to drive anyone mad. Now the question probably is, how is this related to the notes today on the photoelectric effect? So I guess your goal is to try and see the correlation between Sisyphus's task and the photoelectric effect. So there's a source of UV or light or any kind of EMR, and it strikes a metal surface. In this particular case it's zinc, but it could be copper, cesium, anything really on the metal side of the periodic table. Now when this plate is struck with an EMR, it would excite electrons, causing them to be released. So really what you have is energy going in the form of EMR hitting a plate, a metal plate, and then that energy is being transferred into kinetic energy of electrons moving. Now, as you might suspect, the reason why we're going over this particular apparatus or experiment is because it creates problems with people who follow classical physics. There's a peculiar anomaly that classical physics can't explain and quantum mechanics can. Now, if we look at this little apparatus or experiment here, we can see that we have light of a particular wavelength striking a surface, a metal surface. In this case, it's a sodium. And after it strikes the surface, it causes the release of electrons. Now, you'll notice that if we increase the intensity, more electrons, so brighter light, we make the intensity less strong, less electrons are released. Now the anomaly is, when you change the light, so down here around green, we see the electrons are released, but they're moving slower. And when we get down here around the orange-yellow light, nothing happens, which is weird. So maybe it's just not getting enough energy. So we crank up the intensity so it's getting tons of energy, tons of waves, and still nothing. And this is kind of peculiar, because why is this not producing any electrons? Yet if I crank down the intensity so it's really dim light, this still will. Now what I'd like you to think of is Sisyphus's task and him having to roll a boulder up a hill. Now to explain this anomaly, we actually have to go to Einstein and his explanation. Now if you remember from previous lessons, Planck and Einstein had the ideas of quanta, quantums, or photons, the idea that energy traveled in packets. So here's Einstein's theory. Like Sisyphus, waves carry boulders or energy in little packets trying to get up a hill. If those packets don't have enough energy, they never reach the top of the hill. They just simply go up the hill to a certain point and come back down. Imagine rolling a boulder up the hill instead. You have to have a certain amount of energy to get to the top so that it kind of crests the hill and then rolls down the other side. It doesn't matter how many times you throw that boulder up the hill. If you don't have enough energy to reach the top, if it doesn't have enough kinetic energy to get that far, it'll always roll back down. And it doesn't matter if you throw all the time, so that there's a high rate in which they are rolling up the hill, so that means like a high intensity, they'll still all come back down. Yet if you just take one and throw it so that it does have enough speed or energy, kinetic energy, to get up and over that hill, it'll cause electrons to be released. This is completely different than the idea of waves, where it's a continuous flow of energy. Theoretically, if it's waves, the waves are always going to reach the top of the hill, and it's just a question of the energy building up, like filling a glass of water. You can fill that glass of water fast or slow depending on the kind of light you use and the intensity in which you pour, but the glass is still going to get full. With the particle idea, if you don't have enough energy to flip the particle up into the glass, it'll never get full. This is the idea of energy traveling in the form of packets of energy, which of course is the idea of quantum mechanics. Now of course we're going to have to see some good mathematical evidence behind this to support this in order for it to be accepted as theory. Physicists love it when you can produce a theory, test that theory, and provide evidence that supports it. We're going to look specifically at this evidence in the next lesson, the graph related to the photoelectric effect. So that's it on the basic concept of photoelectric effect. We'll see you on the next lesson when we do the math.